In this problem, I'm going to compute the force applied on one of the plates of a parallel plate capacitor, but I'm going to use the potential energy concept to compute the force. All right, I'm going to show you how, but let's first introduce the variables. We have two parallel plates with the same area A, and D is the plate separation, and we just charge this capacitor, so that means one of the plates has charge plus Q, the other plate has charge minus Q. Okay, so let's describe how we solve this. We basically have this kind of a situation in here. We have a positive plate and a negative plate in here. So we know that this is basically Coulomb's law, at least the qualitative form of the Coulomb's law. So the different unlike charges attract each other. So as a result, I expect that these two plates are basically pulling each other. So there's a force applied in here. So as a result, it doesn't matter whether I compute the force applied on the positive plate or force applied on the negative plate. So I'm going to find the same magnitude, and hopefully I'm also going to find the correct direction. All right. So let's see what's the method involved in here. So let's remember that the force, there's basically an electric force in here, and the corresponding potential energy is related like this. The x component of the force, for example, is equal to the time, the derivative of the potential energy with respect to that x coordinate. It's not a time derivative, sorry. It's a position derivative of the potential energy, and there's a negative sign in here. So this is for conservative forces, obviously, and this is the potential energy associated with this force, and that's the corresponding force. Here, the electric force is the conservative force. This is the electric potential energy, and that's the force. So to be able to use this method, I need to somehow introduce an x coordinate. So I need to have a reference frame. So I'm going to choose it like that. So I think I'm going to use this pink color for that purpose. So I'm going to choose my x-axis to be perpendicular to the planes. It's along that direction. I'm going to choose the origin at the place where the positive plate is, and the position of the plate, the negative plate, is basically equal to the separation in that case. So I'm going to use x in here because I would like to basically use this expression in here. So as a result, for a while, instead of the variable d, I'm going to use the x variable. Okay. So as a result, for now, I'm going to call all the separations as x. In any case, somehow, what I need to do is I need to write down this potential energy as a function of x, therefore, and then I'll take the derivative, and since the force, I expect the force to be equal to be in the leftward direction for this plate, I expect to find a negative value of that force. So let's just keep this in mind. Right, let's quickly write down the potential energy. Here, this is not the potential energy of the negative plate only. It's the potential energy of the whole system. But I can use the potential energy of the whole system to find a force on the negative plate. All I need to do is to see how this potential energy changes with the position of that negative plate, right? Let's go ahead. So I have these three possible expressions that we have discussed in class for the potential energy of a capacitor. Okay, I can use either one of them. Any one of them would be okay because they are all equal to each other. However, in our problem, there's this constraint in here. So I have just charged the plates with a certain charge Q, and I'll be looking at a situation where I'm changing the distance, the separation between the plates. But I would like to, in that case, I need to actually make sure that this variable in here, which variables do not change and which ones change. So that's important in here. So since Q is well defined, it's given in the problem, Q is fixed in here. As I move these plates away from each other, that charge doesn't change. but the potential difference changes, so therefore this V changes with X. It's also dependent on X, but Q is not. So as a result, I'm going to use this last form in here because I express everything in terms of some kind of a constant that's given in the problem. So I'll just do that. So I'm just going to use this expression. And next, I need to use the capacitance expression. So let me quickly write this thing down. So C in here is epsilon 0 plate area divided by X. Okay, so when I do this, I'm going to get this. So it's Q squared divided by epsilon 0 A divided by X. So therefore, this is the potential energy expression. Just keep in mind that X is the only variable in here. Everything else is a given quantity. I will actually compute the value of that expression when X is equal to D. That's also given, but here it is a variable. Right? Let's see that potential energy as a function of position has this linear behavior. So it increases when X increases. So we know that force is in the direction of decreasing potential energy. So yes, the force has to be along the negative X direction. In any case, let's just cut the story short. Just compute f of x, x component of the force. So that's the derivative of u with respect to x. So that's very simple. It's q squared divided by 2 epsilon 0 a. Okay, so that's the answer to that question. In terms of the givens, the force applied on the negative plate is this. It has the correct sign. This corresponds to a force which is pointing in the negative x direction. It has the correct sign. Sorry about this. This was area A. And it also depends on all the quantities given in the problem. It doesn't appear to depend on the distance, the separation between the plates. So as a result, I'm going to leave it like that. Okay, that's the end of the problem. However, I would like to actually write this force expression in terms of the electric field between the plates. So let's just remember this. The electric field between the plates is sigma divided by epsilon 0, where sigma is the surface charge density, is Q divided by A. So I'm just going to do it like that. So there's a Q squared divided by A in here, but 1Q divided by A, I'm going to define it as sigma. So if I do this, the force expression becomes, it is minus Q sigma divided by 2 epsilon 0. And now sigma divided by epsilon 0 is the electric field. So therefore the force is equal to minus 1/2 Q times the electric field. So we still have the same thing. However, there's a strange problem in here. So I have the charge in here is equal to minus Q. However, the electric field in here is sigma over epsilon 0. And in another chapter, we have said that the force applied on a charge is given as, let's write it down like that. So that's it's the charge multiplied with the electric field, right? So as a result, if I write this thing down in here, so that's the x component of the force is equal to the charge, which is minus Q in here, multiplied with the x component of the electric field, in which case this is positive. So therefore, we get Q times sigma divided by epsilon 0. Okay. However, the correct answer contains a factor of 2 in the denominator. There's a problem in here. So as a result, this is the products. So there are two alternative derivations of the same force. In one case, I get 1/2 of charge times electric field in the leftward direction. So let's say by using energy, but by using this expression in here, let's say by using this, right, this expression, we get this. And the question is, why do I get two different expressions in here? Apparently one of them is wrong. I'm not going to tell you which one is wrong. I need you to find this thing out by yourself. So just think about it. I will just give you a clue in here. One of them is correct. and find out which one is. But I mean, there are some certain things in here. There are some certain assumptions that we made. So this is perhaps the point where you need to reevaluate these assumptions. Okay.